So let's transition from descriptive statistics to differential statistics. Let's talk about statistics where we can actually do something. Now this section is about probability, and it's not a very long chapter in the script I have, and I'm going to try to go through it relatively quickly, covering all of it, but going through it relatively quickly because it shouldn't be the primary focus of this class. I think you should understand probability because it helps understanding how you will prevent errors on surveys and data collection. But I think for abstract sense of mathematics, I think that's not the best use of your time. So don't mind me. Right, so probability. So probability is what, at the end of the day, you're going to use for decision. And because you're going to have to make a decision, and the decision is going to be based on benefit versus risk, for example, or reward versus cost. None of those are constrained by some level of probability and your chances of success. And so we're going to talk about probability in the sense of help to build your ability to make decisions. And so, what is low probability? For example, I have a low probability of winning the lottery. What does it mean? Unlikely, right? So that means it's a rare, unlikely, or unusual occurrence. Okay. Favorite part, the vocabulary. I'm going to go with three things. So I'm going to look at an event. And we define an event as a collection of outcomes from a procedure. What's a procedure? Anything, right? I'm assuming you guys are not from the X, Y, double Z, Y generation where you want something for nothing. You actually are used to doing some work before you get results, right? So there's a procedure. So event is considered a collection of outcomes. Procedure could be flipping a coin or flipping a deck of cards. On that note, I'm assuming most of you have seen a deck of cards before, and if you didn't, take a look at it. I'm assuming most of you flipped a coin before, and I mean a fancy coin that doesn't stand on the edge but goes to the one side or the other. We're not talking about the trick coins or grooves on your table. And the third one is, I'm assuming most of you seen a six-sided dice. If you've been to Vegas and played on a craps table, I'm assuming you saw. So those are three things that we're going to use because they are well defined and easy to relate. Hopefully we're going to build from that to something we can actually apply to bigger systems. So event. Alright, so there's a collection of outcomes, and there's a bunch of outcomes that can happen in our procedure. Then we have a simple event. And we define a simple event as a single outcome. Single outcome and then sample space and just I'm going to box it in because sample space is important. And sample space is all simple events. So if a simple event has single outcome, and we are saying all simple events, means we are looking at every possible outcome. Every possible outcome. Okay. So let's look at an example. Let's look at the procedure, and the procedure is let's flip a coin. We're going to specify we're going to flip it once. What do we want to do? Tails? So let's look at an event. The event we're going to look at is we want to get tails. Heads or tails, so we want to, or a tail. Yeah, we're talking about perfect coin choice one tail. Okay, so what's the sample space? Heads or tails. Head. Oh. Too easy. Let's conquer it. Now why not? We can do it, right? So let's do our second one, and let's flip a coin twice, or 3 times.
Oh my God.
Right? It's twice, thrice. That's how you call it. English is not my first language. So let's flip a coin 3 times. What do we want to get? If you flip a coin 3 times, what do you want to get? Anybody?
Heads.
So I got 2 heads and a tail. Sure. What's the sample space? No.
6.
No, not 6.
Head or tail?
Head or tail is a good start, but then we're flipping it 3 times.
So 6 times.
So it could be 6 heads.
I flip a coin.
But that's why we're looking at sample space, all the possibilities.
So it's 3 tails and 3 heads.
Yes,
Oh, 3.
right? You can get 3 tails, 3 heads. You can get head, tail, head, tail, tail, head, tail, right?
Oh, then you said 9. That's
There is no 9.
None options.
9 options.
8.
Oh, 8.
Yeah.
But, so if you like numbers and you like letters and you like those type of combinations, like myself, you're very good at it. You have your favorite way to do it. For everybody else who might not like the diligent letter after letter over and over again, there's a couple ways to do it. One of them is you're trying to be meticulous about doing so, so you're going to go head, and you're going to go head, and tail. And eventually you might get to it. The third one is a tree diagram. Let's get a tree diagram. And tree diagram looks like this. We flip the coin for the first time. What do we get? We can get a head, or we can get tails. First flip, one or the other. Let's say we flipped a head. We're flipping the coin again, what can we get? Well, we still get a head or tail, so head or tails. And then we got, let's say we got head, and what can we get next? Or we can get either head or tails. Well, what happens if we flip the head and then flip the tail. Can you just do the head and tail?
Sure.
So what do we get? Well, the first attack, we got heads, then we got heads, then we got heads. We got heads, heads. Second one, we got heads, heads, tail. Heads, tail, heads. Heads, tail, tail. Tail, heads, heads. Tail, heads, tail. This one sounds funny with my accent. Tail, heads. Red marker. And the last one, tail, head. 8. So what's our sample space? Well, our sample space is heads, 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 tails, heads, heads, tails, heads, heads, tail, 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 heads, I promise I will not make you write big sample spaces. This is about as big as it gets. Because we could do this for 50 coin flips. It's a science project for kindergarten. It's not for adult people that want to learn. So, but we got this. Do we have this here? 2 heads and tail, or we have some choices. So again, what we did, what's the event we are looking for, and what are the possibilities? There's all the possibilities there. Questions about either the tree diagram or this table? Is everybody comfortable? All right. It's hard to gauge feedback when you guys are all poker face. I know we were talking probabilities and I told you about cards, but all right. So a probability is the likelihood of is that correct? Probability is the likelihood of an event occurring. Well, what's probability? We did algebra, so we are comfortable with the notation of a function. So let's do probabilities as P. Let's do events as an A or a B. Usually big numbers. Usually capital letters are. And so we can define P of A as the probability of event A occurring. All right. Well, this is all fine and dandy. So let's look at some more concepts. So there are 3 types of probabilities. That you will encounter. There's the observed probability. some textbooks it's called empirical. In some textbooks. And that is a probability that is based or estimated on observation. So probability that is estimated. Let's give you an example of observed probability. Okay, how many of you watch sports? Any sports whatsoever?
Mm-hmm.
Say, what's the sports you watch? Soccer. Okay, thank you. Brownie points right there. But how about baseball or golf?
Golf.
Golf? It's not a sport.
Yes, it
But, but say, we can argue, but say any of those single player type sports. Baseball, right, is relatively single player because you're the batter or the pitcher, there's only one pitcher, one batter, right? Or football, right, you have the quarterback. Or soccer, you have the goalie. How do we know that, I don't know, what's his name? I forgot. I was making fun. Barry Bonds. Barry Bonds is a spectacular golf player. How do we know that? Or what sport?
Oh my God,
baseball.
what are you on?
Oh, yeah, baseball. What am I on? BCP mostly, but you know, let's go get that out. But how do we know he's such a good player?
Home runs.
You have some kind of average, right?
Oh.
So what the probability of him hitting a ball is what? 3.7, no, 0.37. So 37%, he has 37% chance of hitting a ball, which by soccer standards is somewhat embarrassing. But you know, when you have a piece of condensed rubber going at you at 95 miles an hour, your life perspective changes very quickly. Right? You have a split of a second react. How do we know that? Did somebody come to me, him talking to pee in a cup, measured the size of his head, you know, the length of his legs, made him run a couple laps, like 37%.
They watched it.
Yeah, they watched it, right? We have over and over, we have the baseball trading cards, and I found in my old Goodwill a bunch of them from 87 to 92, and they have the statistics, and I'm looking at, you know, every year they sit down, they calculate for the season, they calculate for his career, and this is the average we had, and so we are expecting this. Just like most of you didn't expect a quiz today because we had 4 classes, we had only 1 quiz in 4 classes, so by observed probability, the probability of a quiz is 25%. I'm not going to sweat 25%. Right? If it was 95% of getting a quiz, most of you would be like, yep, I'm ready for it. But most of you didn't sweat because the observed probability was 25%. Right? Same with baseball. That's observed probability. Can somebody give me a different example?
4-1.
Sorry?
4-1.
He's talking about golf.
Oh. Oh, okay. No, look. Hole in one, okay. I was like, hole in one. Okay. Sport, and golf, yes. Okay, that you have a probability for that. Either you have a probability for the field or for the player. Good. How about something connected to hospitals?
Or like average.
Expectation of successful surgery, right? There is a
I'm
number
trying to
for
think
it.
of something better than
There's no look. If you have a friend who is finishing their residency, they're probably sweating the fact that they're going to have to spend about 25 grand a year for insurance, malpractice insurance, right? Depending on which hospital they do it, under whose supervision, under which department, and how new the equipment is, that will spike very deeply. My friend from college moved to a different hospital, and her malpractice insurance dropped by 10 grand because there was just not enough accidents in the hospital to merit high prices. Right? How do we know that? Well, you killed people. We know. We have, you know, stones on a loan to prove it. Right? Rest in peace, malpractice insurance. My family is rich for the rest of my life. right? We know that. And this is observed probability. We measure things, we take poll data, and we have this. There's a second probability, which is, I call it classical probability. But sometimes it's called, referred to as theoretical probability. This probability saying that that's based on a chance of an event occurring. Now, most textbooks will have the next piece of this out in the bold, in explicit form. But there's one or two textbooks that I found that don't have this spelled out very obviously, and that's that each simple event must have unequal chance of occurring. And that's important. If we look at this, each one of those has the same chance of occurring. Like if you flip a coin, heads and tails goes there. So that's important. So when you're talking about classical probabilities, we're talking this. That's why A-Rod cannot have a star that is classically proven, because there's no way for us to build this equation. Okay? Classical probability is pulling cards out of a deck. Classical probability is flipping a coin. Classical probability is sure, very good. And then comes the third one, which is my personal favorite. This one is called subjective probability. You got lung cancer, you go to the doctor goes like, you have 65% of surviving next 5 years.
Oh, yeah.
How did he do that? Did he measure every cell? Did he have a meeting with the cancer and negotiate for your life? No, I'm dead serious, right? You come in to the doctors, and the doctor says, well, you should get a vaccine because you have like an 85% of chance of getting sick this flu season. And I'm looking at him like, where's your data? He's like, it feels like 85, maybe 82%.
So like weather, chance of rain.
Rather, or like, I came to my parents look at me and like, how did you do an exam? What's your chance of passing class? And I'm like, 60, 62%. And they're like, where's your data? My both parents used to be a math professor, so, right, so it's like, where's your data? Subjective probability is, at best, an educated guess. And so here we have the tricky part about parts of probability. One is, if I flip a coin once and I get heads, how lucky is this coin? Well, I'm using observed probability. I flipped it, like I did something. I flipped it, I got heads. The chance of getting heads, 100%. I flipped it once, I got heads. For the rest of my life, I'm going to get heads with that coin, right?
This is when you go into bigger number theory, large number theory.
Oh, we're going to get to that too, to large numbers. But, right? So, okay, so I flip a coin 100 times. I get 64 heads. My chances of getting heads on that coin are 64%. Right? I sit in front of the slot machine and I win 2 out of 3 times. Right? 66% chance of winning. That's mentality. Right? Sorry?
In practice.
Oh no, practice. You actually have an actual data set, right? If you flip a coin once, you get heads. The assumption is that you're always going to get heads. You flip it twice, you get heads and tails. It's 50-50. But you get twice heads, it's still 100% heads, right? On the other hand, we have the classical probability. Any of you watch poker on YouTube? Every now and then, right? And they pull cards and they have the river out, and on the side they have percentages of winning. How do they get those? They don't get from observed because the game is still played. They get it from classical. They know how many cards are in the deck. They know that pulling a card, each card has the same chance of happening, right? Unless it's on the table, probability, if you have 30 cards left, pulling one of those to be something that is not, right, that's classical. So pulling a heart, what's the probability of pulling a heart out of the deck of cards? And I mean standard 52 deck of cards, no jokers. 25%. How did you get that?
1/4.
There's 13 hearts out of 52 cards, right? Now, there's a common mistake where people say, hey, there's 4 suits, right? So I'm going to pull, no, but there's not 4 choices. Every simple event, which means that we are looking at the sample space. The sample space is the 52 cards. So 13 out of 52, 25%. Right? That's classical. And we're going to continue that thing next week.